Okay, so we've just seen it draw the Mandelbrot set. Very satisfying. The colors are still a little off. And if you look at the source code, you'll see it's a really tricky part. Sophisticated, advanced Mandelbrot programs that you can buy in the shops for thousands of dollars will have the option of actually putting in different color palettes. So you don't have to go from blue to red, what have you. You can choose your own, and you can make beautiful pictures. And in fact, that's how the Wikipedia stuff is drawn. But they're so intense, and I don't know. Now, I showed you this stuff, we went through these pages, but we missed out on all the beautiful pictures that come later. Not that one, although I was tempted to do that in class yesterday, just the stars. Okay, that's boring, black and white. Black and white, who wants to see that? But then, okay, this is the Julia set, so this is different. And this is not all pure Mandelbrot. It's also mixed in with, if you decided to start working. No, I think it's a battery though. Okay, right. They've also mixed in other kind of variations, but most of these pictures are from Mandelbrot. So that's zooming in. Oh, very psychedelic. Just look at that. Once you start playing with this, you'll soon realize that, okay, there's a limit to how exciting this actually is. It's not. Anything else? And Mandelbrot is not like pi. If you take the pi expansion of pi, you can find any sequence of digits in pi. So you can take your date of birth, and eventually somewhere in pi, your date of birth will appear. Or you can take your social security number or South African ID number, and somewhere in pi, that is contained. Pi contains all the information that exists in some sense. And in fact, another nice program is to find out where in pi is my date of birth. There are techniques for doing it really, really quickly. But Mandelbrot is different. When I first saw the zooming in, I thought, oh wow, maybe all possible images is somewhere in Mandelbrot. And if we just zoom in close enough, we'll find an image of everything. Anything you want. Oh, there's a three-dimensional Mandelbrot. Looks a little sick. Okay. But that is not true. So I just picked one point just to show you that you can zoom in. So I made a few changes to this program, but they should be pretty clear if you look at them. And one thing I added was the parameters. Hi, ek dink it's dalk net die battery. Maybe it's just the battery that's flat. I didn't check. But it's not working. It's on. Okay, uitstekend, dankie. Just for my own recording, the class mic is broken. I'm not huffing and puffing for nothing. Okay, so what I did put in was the limits of what we're drawing, the coordinates of the bottom left and the top right point, and we can change that to zoom in. I'm not sure, I know. I'll show you in a second. So we can draw any set of coordinates we want. That's the original. But I've just changed the parameters, and here is a zoomed in part of Mandelbrot. Okay, not extremely exciting, but a little. It looks like what? Frozen. I know for a fact, by the way, that the movie Frozen was inspired by the Mandelbrot set. Yes, absolutely. Another true fact. Don't thank me. No. No applause, please. Okay, right. Can I open my init key? Let's just see. Can I sneak in my init key? Yeah, cool. So I guess if I Google Mandelbrot viewer, Look, the excitement is not the Mandelbrot set at all. That's rubbish. The excitement is doing it yourself, writing it and seeing that it works and tweaking it until it's absolutely perfect. And that's the most important part. This is an online program, obviously, that will draw the Mandelbrot set for you. This time using a different palette. And what my program lacks, and which I'm not going to add because I'm now bored with it, is the ability to zoom in interactively. You'll also notice that this program uses a slightly different algorithm that makes it draw the set a little quicker. Met 'n glas of suig. Okay, kom ons af. Aan. Is it the frequency? Oh, there we go. I was just using the wrong voice. Thanks. Bye, donkey. Okay, right. So a little quicker on the draw, but still kind of satisfying. Okay, now I want to find Mandelbrot again, but I don't think it's... Where are you, Mandelbrot? Okay, I think we've kind of reached the limit of this program's not of its precision. So it's using real numbers, obviously, and there's some limit to how far this program can zoom in, but of course the set goes on forever. Or maybe it'll refine it, maybe not. In any case, that's Mandelbrot. So that's tick done. What we are supposed to talk about today is something entirely different. And let's just go back to page 1. Okay, right. Okay, right. So we are supposed to talk about modular programming. This is not exactly theory, but it's getting a little closer. We're going step away, just one step back from... okay, now it's an autoplay. It's not what I wanted. Okay. We're one step back from programming, from writing actual code. But this is important stuff to know. And once you're a programmer, this is something that will kind of play in your mind. Because we are learning programming in the small, writing actual code. But once you've mastered that, you move on to programming in the large. I now know how to write code. How do I put all these pieces of code together? Modular programming is a name we give to an approach. The idea is that we're going to, and I've told you this before, we divide our program, our big program, into separate little pieces that all function somewhat independently. So they're all self-contained. We can attach each one on their own, and we combine them to make the big program. So instead of using a for and an assignment and a while and an if statement, we're now going to use that module and that library and that library and that library. It's one level up. And once you've mastered that, you go one level up again and say, okay, I've got that piece of software, and I've got that piece of software, and my organization has these pieces of software. How do I combine them? How do I integrate all these different pieces of software? I have a mail program that our business uses. I have, sorry, just going to switch this little thing off. Before my alarm to wake up goes off. Oh, that's fine. I've got an email program in my organization. I've got a spreadsheet. How do I connect the two? How are they going to work together? And these days, they may come like that automatically, but they may not. So here is an example, but I don't really want to work through it. It's just an idea of you flip a number of coins, and you count how many times you get head and tails, and then you plot the distribution. Do this over and over and over. Simulation. And this program that implements the strategy is actually implemented, well, here's the main program, but it's using a lot of libraries. It's using standard, random, it's using the integer library that we know. It uses standard stats that we haven't looked at, but it exists. It uses something called Gaussian. There's math.square root. So lots of libraries are being used. And in fact, the whole program structure is a little like this. Bernoulli is the main program. It's using integer, the parse routine. It's using this library, standard stats. It's one of the libraries that come with the books, that comes with the book. It's using standard stats in turn uses standard draw to plot that histogram. And it's using standard random, which uses math.random, all that stuff. And the fact is that all these libraries were written independently of Bernoulli. Nobody, when they were writing standard stats, said, I'm going to write a Bernoulli program eventually. They said, I want to write a library that will allow the user to plot various statistics. And when people were writing math, they didn't say, I'm going to write this so Bernoulli can use it. I'm just going to write a general math library that will be useful to loads of clients. And when we wrote Bernoulli, we decided to use it. So I can build a complex program from all these simpler parts, in some sense. They're all simpler than the whole. I want the structure in my code. One thing I do not want is to put everything I write in one big file. And inside each file, I want to program in a structured way. I want to write nice ifs and nice whiles, code that other people can read. That is something else. That is called structured programming. In the early days, when computers were invented, how were they programmed and what languages did they use? The very first computers, well, yes, in a sense, the very first computers had very simple instructions that you had to enter one at a time. So I've got a program of 5,000 instructions. I'm going to input my instructions one by one. And how you did that was not by typing them on a keyboard, because there was no keyboard, and there is no screen. What you had was a console. I wonder if I can find a picture. A console where you toggled a lot of switches in binary, and then when you toggled the code for the next instruction, you push a button, and the machine accepted that and stored it in its memory, and then you'd enter the next instruction. Instruction, enter. Instruction, enter. Instruction, enter. And when you've done it with 5,000, you press another button to actually run what you've just entered. Maybe I'll show a picture on Monday, because I had one last year, but I don't think these slides have one. That definitely got out of hand when people started writing more ambitious programs. You can't do it that way. And in the 1960s, well, in the 1950s, they invented programming languages. The earliest programming language is called Fortran, and there's another one that's equally old called Lisp. And using these languages, people started writing programs. But once again, no idea of modules or modular programming, all one big program. The more powerful the languages got, the more ambitious the programs people started to write. And in the 1960s, they realized that they can't go on like that. There was something called the software crisis. The software they were trying to write was getting too complex for one human to understand. If you have 1 million lines of code in your program, and you realize that there is a bug somewhere, where do you start? Well, that's fine. You know the program, you wrote it. You can probably put in a few print lines and see where the bug is. What if it's somebody else's code who was just hit by a bus, and now you have to take it over and find their bug? Where do you start in their 1 million lines of code that you've never seen before? Say again?
How is the 1 million lines of code presented?
It's in one big stack of punch cards. So one line on a card, all the characters, and if you drop it and they become shuffled, you have to resort them and by hand and put them in the right order. So don't drop the program. Why do what? No, you get little boxes that you put the punch cards in, and if you wanted to, how do you create the punch cards? There's a separate machine for that. There's one in our foyer. And you sit at the machine, you insert your punch card, you type the line you want to appear on the punch card, and it'll punch it out.
So can you then, I only imagine the function of this thing is that there's some other machine that can read these punch cards.
Then you take your box of punch cards and you go to the operator. So at this university, the operator used to be in that building they're now renovating behind this building, the next one. And on the second floor, there used to be a little counter with a little glass window, and there'd be operators behind it, and you'd say, here's my program. We'd stand in the queue, because all the other students also want to submit their project tonight. So you'd stand there in the queue with your project, and or box of punch cards, you'd hand them in, the operator would load them, you'd get your turn on the one computer that we owned, and it'll run during the night, and tomorrow morning you can fetch a printout of what your program has produced. Okay. When was this? In the mid-80s?
Sir,
Yes.
how many people would Stellenbosch have been employing at this point if so much what we were doing was like based around stuff like that? Like someone had to do that for you. I mean, obviously.
Do what for whom?
I mean, I'm just trying to think of like the economy just for a second.
The economy.
Yes.
This is not a course about economics.
Please, but just for a second, humor me. Surely Stellenbosch University must have been employing a huge amount of people.
To do what?
I mean, we don't have operators anymore. That's a start. How many other?
There were 2 operators.
Okay, fine. Continue, whatever.
Postgraduate students used to volunteer to work during the night, but during the day there just used to be 2 operators. I mean, it doesn't take much, and most of the time it's idle. Most of the time students are in class, taking lectures, learning how to make the punch cards, and not queuing at the window. It's only at crunch times when the system goes really busy. And then, of course, you'd be queuing for an hour or 2 hours. You'd almost get to the front of the queue, and some professor would run in and say, oh, I've got an urgent task. Please prioritize this. And I'd jump the queue and give it to the operator, and you'd have to wait another hour. In the late 80s, the first computer lab was built at Stellenbosch. That was Furga right at the back. I guess you guys have not been there, but it's huge. It's huge. Okay. It's bigger than this room, full of computers. And eventually we got more and more labs and personal computers. But back to structured programming. They realize that there is a software crisis. How are we going to write big software? And this idea of modular programming, first structured programming. Write a program neatly with structures like whiles and ifs and fors that everybody can understand. Because at that time, programming languages still had other statements that were not good. Not good meaning bad. So here is an example. This is Java, but enhanced to include, where's the pointer? No pointer, that's fine. I'll point with my mouse. Enhanced to include something called a label. So you can label statements whenever you want. And then you can have go-tos that'll jump to that label immediately. So this code says int n is integer.parse int arg0. Fine, we can do that, the first command line argument. N becomes n plus 1. I can make it 1 more. If n is now a multiple of 5, go to label C, where it decreases n by 2. Label E decreases another n once more. If it's now a multiple of 4, go to label A, where it'll start increasing again. But if it wasn't a multiple of 5, if it's a multiple of 7, go to label B, which is down here, and that just stops. Okay, fine. Otherwise, if it's not 5 or 7, increase it, then we're at label D, multiply it by 2. If it's more than 10, go to label E. This is the one that decreases and checks. Okay. So what does this program print? Let's say if the input is 27. Well, you don't know. I don't know. This program is too complicated to understand and not worthwhile. The way that we can jump all over the place, this is called spaghetti code, because this looks like spaghetti once it's been cooked, I guess. I hope not the pre-cooked version. Our programs look like pre-cooked spaghetti because it's nice and straight, but these things go all over the place. And it's very difficult to predict what the program prints. For 0, it prints 3, 2, it prints 7, 3, it prints 9, 4, it prints 4, 5, it prints 15, 6, it prints 7, no pattern. And what's more is for 1, it doesn't even terminate. So it just keeps on going around in its loops forever. This was the kind of software that people were writing in the 50s and 60s, even the 70s. And this is what we want to avoid, which is why Java doesn't have a goto or a label statement and shouldn't have one. Okay, right. So what do we need to know about this modular programming? We need to know that, or structured programming, we need to know that there are some control structures that the only ones we're going to use, and we've seen almost all of them. Sequence, statements are written one after the other in sequence, and that's how they're executed. We have selection. We can make choices, branches, where to go, left or right. Is something true or false? Which way do we go? And iteration. Let's repeat something a couple of times. And once you have those three, you can write any program. All programs can be written with these three statements. In fact, all programs can be written with, my mistake. All programs can be written with assignments and gotos and ifs. We don't really need repetition if we have a goto, but it makes the code so unreadable that we want these structured iteration, structured repetition keywords. And then recursion will start on Monday. It's another, you don't need that, but it's an important control structure in computer science. Then we have subroutines that we can call. Where do subroutines come from? So very theoretical today. When was the first computer?
It's been forever, right here.
What is a computer?
Something that takes input and gives out.
Is there a computer in my watch?
No, because your watch is mechanical.
Well, the display is analog. Is it a smartwatch? No. As it happens in this watch, there is no computer, but most watches have computers. Well, smart watches have more computers than we used to land on the moon, everybody always says. Is there a computer in your microwave?
Yes.
Are there computers indoors? Well, it's not inside the door.
Well, no, but it's being operated.
But there are computers with doors inside. If you go to a hotel and you put in a key card.
Computers with doors inside.
No, well, there are computers with doors, but there are doors with computers as well. Is there a computer in your dog?
Probably not. Unless they
Is an RFID chip a computer? What is a computer? Who knows? So, modern computers, we say that the very first prototypical computers were things like the Jacquard loom, which was invented in the early 1800s, and Babbage's machines, which were mechanical machines that could execute programs. And even then, when Babbage, this engineer in Britain, invented these machines, which he actually never built because he couldn't, at that time there wasn't enough technology to build the cogs to enough precision to make the computer itself. And in fact, Babbage spent all the money he got from the government not on making the computer itself, but on building the tools to create the cogs that it needed for the computer. Eventually he ran out of money, and he was also a kind of crazy guy. He invented the locomotive cow catcher. Say again? It is fantastic. It saved lots of lives, cow lives. If you have a locomotive, a steam engine, at the front there is a little skirt. Have you seen that in old Western movies? That's called a cow catcher. It's so that cows on the line won't impact and ruin, go under the wheels of the train, but in a way that I'm not entirely sure how it operates, will be flung away from the locomotive as it approaches at high speed. YouTube, I'm sure, has many such images. Now, this is entirely unrelated to computer science, but trains themselves are fascinating. When the first locomotives were introduced, they were afraid that because of the high speeds, up to 50 miles per hour. How much is 50 miles per hour? Let's say 80. Of these high speeds, people will be decapitated just by the air pressure. At this stage, the locomotives, the carriages were open top, so like top down. And people still dressed up in top hats to go in locomotives. Not entirely relevant to structured programming. So Babbage made the first computer, but then the real first electronically stored memory computers were invented in the 1940s and 1950s even. But even Babbage's mechanical machine had this idea of subroutines, that there's something you want to do over and over, so store it in some place, and when we need that function, like calculating the sign of a number, we invoke it and we can call it again and again. So subroutines are really old, more than 120 years. And in Java, of course, that's our methods and functions. And then there are modules. We haven't seen packages yet, but we've seen class. So we put all our code inside a class. Our code for our main program, our code for our library, they're all inside separate classes. Structured programming, really important. Well, how does it help? Well, there is this idea of concerns. If I'm writing a piece of software, I have many concerns about the software. I want it to have the right functionality. I want it to do what I want it to do. But there are also other aspects of the software I want. I want a nice user interface. I don't care if Mandelbrot produces an image file, if that's what I'm really after. But it's nice for it to have a nice interface. Maybe my software has to talk to other pieces of software, like on a network. My project has to talk to other computers, and then I have to use networking. That's a separate concern that's slightly different from the required functionality. Then there are things like testing. Can I test the software sufficiently? Can I log what's going on, so when something goes wrong, I can actually go back and see what did the program do? We want to separate these concerns into separate modules, but that's not always possible because sometimes there are things called cross-cutting concerns. Logging is one such thing. It probably has to be everywhere. I probably also want to log the functionality and the user interface because I can have problems there as well. Testing the same. I want to test everything, not just the functionality, but the interface, how it works with other things. So separation of concerns is a term we use to say that is the motivation for structured modular programming. We want to separate our concerns into separate modules, separate packages that we can combine together. Once we've done that, there is a way for these modules to interact. So there are two measures of how well did you actually achieve modular programming. One is called coupling, and one is called cohesion. Cohesion means how, if I look at one module, how well does it hang together? Does it do only one thing? Or does it do a lot of separate things? I want the module by itself to be cohesive. It has one concern that it addresses, and that's all it does, and it does it well. So I want little cohesive modules. Then I want low coupling. Coupling is the interaction between two different modules. We've got a module A and a module B, and they can make calls to each other or from each other. I want that to be as low as possible because this is a bad situation. I've got high coupling. They are very strongly connected, but low cohesion. These routines, only these two call each other, and they're called all from different places. So this is a bad situation. Why do I want low coupling? If this module has to be replaced, maybe it gets a new user interface, maybe one of the API parameters changes slightly. If it's called from a lot of places in other modules, there are lots of other modules I have to update to replace this one module, this one. So if I have high coupling, it's highly coupled to the other modules, then that means a lot of work. And it's also difficult to understand this module. I have to go and look at all the other places. How is it used? If I have to replace it, what can I do in those places to change? This is a good situation. It's got high cohesion, so the functions inside this module call each other a lot, and it's got low coupling. It's only called from a few places. So this is what I want. Low coupling, high cohesion. This is bad. High coupling, low cohesion. Right. So we are learning a couple of terms here. There's modular programming, meaning I want to separate my program into different individual units. There is structured programming, which is the kind of code I write inside each module. There is separation of concerns, which is the motivation for doing a structured and modular programming. And then there is this measure of how well am I doing. And if you're in a big organization, let's say Microsoft, this is something you'll measure physically. So there are formulas for measuring. What is your coupling factor? What is your cohesion factor? And if a team writes new software and they've got high coupling and low cohesion, we can point that out to them and say, you've got to refactor your software to improve the cohesion and coupling numbers. Okay, and this last thing is called abstraction, which is also called information hiding. It's the idea that I write a module with lots of dirty details, but I don't want to expose them to the outside world. All the outside world sees is my API. This is an abstraction of what my module does. Here is the actual implementation, and that can be down and dirty, but the API, parts that are public, that other people can see, is really hidden. Oh, sorry, it's not hidden. The details are hidden, but this is the only public part, which means that if I find a new way to implement Mandel, I don't have to rewrite all these clients that are using my software. That can stay the same. The API can stay the same. I've hidden the implementation inside, and I can change that at will. Sometimes you do have to change the API a little bit. And that's usually when, for a library, the version number gets changed. So the API protects clients from changes in the implementation. Oh, beautiful. Programmers can improve the implementation without affecting the clients. So we can make our software better and better and better, but with very little work, because only one module is changed. Is that the last slide? Yeah. Okay, right. So let's just go back a second. I've got to stop. Here's my Mandelbrot class that I wrote last night. This is not a good class. Main is public. It needs to be, because this is my main program. And Java requires that the main program contains public static void main. But all the other stuff here, they don't need to be public. They can all be private. I know we've talked about this before, but let me say it formally again. If it's public, everybody can see it. If it's private, I can only see it inside this one module. So I'm going to try to always make everything as private as possible. No need to know the bounds. No need to know the radius or infinity's value or any of that stuff. So now I'm left with one single public method, main, which is what this program requires. It's not a great example because it's not a library and it's not going to expose anything except main. Okay. I have to stop. What will I do on Monday? Should we just start recursion? I'll show you a picture of a cow. No, I'll show you a picture of the original computers and how they were operated. And then we start recursion. You can watch cow video in your own time, because I think that's a kind of specialist interest subject. As it's called. Yeah. Before you go, very quickly, Afrikaans, modulaire programmering of gestructureerde programmering. Dit is krities vir rekenaarwetenskap. Dit is nie die beginpunt van die onderwerp nie, maar dit is beslis sedert die laat 60s 'n baie belangrike idees wat in rekenaarwetenskap ontwikkel het. En ons werk nog steeds daarmee. Nuwe programmeertale het nog steeds nuwe konsepte wat hulle uitprobeer vir hoe om gestruktureerd en modulair te programmeer. So daar's hierdie konsepte wat genoem word gekoppeldheid en kohesie, en ons wil graag hê dat programme laag gekoppeld moet wees, so die modules is relatief onafhanklik, maar hoë kohesie moet hê. So binne een module dit is baie meer samehangend as wat dit divers is. En hierdie idee van om inligting weg te steek, abstraksie, is krities, want dit laat ons toe om die implementasie van ons kode te verbeter en te verbeter en te verbeter, sonder om die res van ons sagteware te beïnvloed. Ek dink hier is 'n bietjie van 'n gebrekkige vertaling. Opsomming, maar miskien moet ek begin om slides te maak vir hierdie opsommings. Hoe dit ook al sê. I'll see you again on Monday. Monday is still a Monday. Just a gentle reminder. Monday is Monday. Tuesday, Wednesday. Thursday is a Friday. Okay, Friday schedule. Just remember that. Okay, cool.